Hello everyone and welcome to this new video of the LTSpice part of the Circuits and Systems course. You have recently seen the transient regimes for several circuits in the theoretical part of the course with Mr. Rashidi. Here I have given you the equations for the RC circuit. The RC circuit is characterized in particular by a time constant τ equal to RC. I remind you what a time constant is with this definition that I read in a physics dictionary. In physics, a time constant is a quantity homogeneous with a time, characterizing the speed of the evolution of a physical quantity in time, particularly when this evolution is exponential. For this exponential system, for example, the time constant is the time it takes for the exponential argument, here, to be equal to -1. That is to say, that the time t in the numerator is equal to the denominator. For the RC circuit, it was RC, but it can be anything else either. On a graph, this time constant appears very clearly. Here we have a function of type 1 minus exponential of t over tau. You can see that after a tau, the measured value reaches 63% of the value at infinity. Why 63%? Because if you make 1 minus 1 over e, so 1 minus e to the power minus 1, you get about 63%. This characterizes the evolution of the system quite well, because as multiples of the time constant occur, this magnitude tends exponentially towards its value at infinity. With the time constant, we can characterize where we are in this evolution towards infinity. Due to the analytical properties of the function shown here, the time constant can be measured graphically very easily. Indeed, the tangent to this curve at time 0, if we trace it, gives us here the time constant τ. You can derive this function and you will easily see why. We will now look at RC circuits using LTSpice and see how this software allows us to study the time constant. Here we have drawn an RC circuit. This is something you can do well with the experience you have. We are going to analyze it by means of the point run function, so for the transient regime, for 1/100th of a second. You also know this function because it has been used in the previous videos. On the other hand, the way we have configured the voltage source will be more foreign to you. We have configured it in pulse mode, which allows us to generate pulsed voltages, that is to say, voltages that change very quickly. We need an initial voltage. Here we have 10 volts, a voltage when the pulse is on. Here we have 0 volts. This allows us to simulate a circuit which is under 10 volts of voltage and which has suddenly changed to 0 volts. It becomes a kind of short circuit because an ideal voltage source at 0 volts can be replaced by a short circuit. We must also configure the time t rise and t fall, which are in fact the time it takes for the voltage to go from the initial state to the on state and back again. Ideally, it would be 0 nanoseconds. In the real world, it would be a little bit more. These parameters are mandatory in LTSpice. Normally, as the pulse is designed to be a periodic function, we also put the t on, which is the time during which the pulse is in state on, but for the moment, what happens after the transitory regime does not interest us, so I put a period compared to which the duration of our analysis is negligible. Now that we have done all that, we are going to turn on our circuit and measure, for example, the voltage at the terminals of C1 as well as the current flowing through it. Quite quickly, we see some interesting things on this graph. For example, the voltage that is at 10 volts when the circuit is on goes down exponentially to 0 volts, and the current, here I will adapt the scale to 0 amperes, that was at minus 10 milliamperes, goes up to 0 milliamperes. Why minus 10 milliamperes? Because the capacity discharges, so the current goes into the opposite direction, here from bottom to top, whereas we measured it from top to bottom. We can see that at the beginning the absolute value is quite high, and that it goes down exponentially towards 0. We can also see on this graph quite easily the time constant. On this graph, the time constant would be the time it takes for the voltage to reach about 37%, 1 over E, of its initial value. If we measure this with a cursor, when we are at 3.7 volts, we are at about 1 millisecond, and this corresponds well to the equations since we had a resistance of 1 megaohm and a capacity of 1 multiplied by 10 power minus 9 farad. So, if we multiply both to find tau, which is equal to RC, we find 10 power minus 3 seconds. What is interesting is to check what this means in terms of unit by expressing ohms and farads in IS base units. You will see that we do indeed arrive at seconds. We can do the same reflection with the current, which also takes a time constant to reach 63% of its final state. We can also say that at the beginning we had 0 volts, that afterwards we switch to 10 volts, and what do we find on our graph? I update with the run command. Here is a voltage that rises exponentially from 0 to 10 volts, and a current that is first very high in absolute value, because the capacity really needs to fill this voltage deficit very quickly in relation to the final voltage, and which also decreases exponentially. Now, on my oscilloscope, I draw a tangent line. It's a bit handmade, so it won't be super accurate. A tangent line to the curve at 0 milliseconds. I do the same thing on the other curve, and I see that these two tangents arrive more or less at 1 millisecond each, so the time constant. If, for example, I change the value of the resistance, I double it, the time constant should logically be doubled. And this is exactly what we observe. If I make the tangent here, I arrive not at 1 but at 2 milliseconds. So, all this is very much in line with our equations. Now, we are going to see another way of using these transient regimes, in really pulsating tensions. Here, I have prepared a small circuit for us. The difference is slight. It is here. We have the same initial value, the same on value. I simply create a periodic square signal. It's on for 10 milliseconds, it's off for another 10 milliseconds. So, T on equals 10 milliseconds and T period equals 20 milliseconds. I am analyzing this circuit for a tenth of a second because we are going to take a few periods to analyze what's going on. To begin, I show you what a pulsed voltage is, which is actually 0 volts, 10 volts, 0 volts, 10 volts, and so on until infinity. I am now measuring this voltage, the same as before, and this current, the same as before as well. You can't see much if I put everything at the same time, that's it. I can see that the voltage at the terminals of the capacitor oscillates to follow the voltage of the source. First, we have the 10 milliseconds that our source turns on, then the voltage at the terminals of the capacitor increases exponentially up to 10 volts, decreases to 0 volts, etc., etc., etc. And each time we let the capacity be almost fully charged up to 10 volts. Now let's pay attention to the current. I might change the color because this dark blue is not very visible. We can see that the current, as before, is still initially very high in absolute value and decreases exponentially in absolute value. Sometimes it just goes in one direction, sometimes it goes in the other. That is why sometimes we start in positive and sometimes we start in negative. Here the capacity is charged, here it is discharged. That is why sometimes it is positive and sometimes negative. What might interest us now is to ask ourselves what happens if I don't give the capacity time to charge. We have the same circuit as at the start, so the time constant is also a millisecond. Now I put 2 milliseconds on and 2 milliseconds off for a total of 4 milliseconds. You don't see much. I will remove the input voltage and put the voltage across the capacitor. You can see that the capacitor never has time to charge up to 10 volts and it also has no time to discharge down to 0 volts. Obviously, because the behavior is exponential, it could never reach these values, but when it gets very close, it is said to have reached it. If we wanted to, we could calculate all this with our equations. So, the period is too small in relation to the time constant. It's slowed up to that point approximately. If I put the cursor, I look at the maximum value, it is 8.63 volts. And if I make 10 minus 10 times e at the power minus 2, I find 8.64, which is very close to our 8.63. Why is that? Because we only let the system charge for 2 time constants. As the loading is exponential, as soon as we leave a little more time constant, I think 4 or even 3, let's try 3 time constants, we would have a behavior already very close to the final behavior, because we let the loading take place for quite a long time. Here we see clearly the exponential shape and the voltage which arrive almost to 10 volts and 0 volts. So we are arriving at the end of this video. I propose you to explore a little bit LTSpice in these transient regimes to see different types of circuits, different time constants, different measures that you can make in relation to your lessons and exercises to plunge yourself a little in a practical way into these differential equations which can seem at first sight rather complicated and which finally describe rather intuitive behavior. That is to say, capacities, inductances, which load and unload. Don't forget these two absolute rules: no voltage jump in a capacitor and no current jump in an inductor, which you can see very well when analyzing circuits with LTSpice. Perhaps there will also be an exercise with LTSpice on this subject. So have fun with LTSpice. Thank you for your attention and see you next time.